To begin the presentation, press the Start Broadcast button on the GoToWebinar control panel to allow all attendees to hear you. This system will notify you once you begin your broadcast. The broadcast is now starting. All attendees are in listen-only mode.
All right, let me take a break of 10 minutes and be back by 9:03. All right, thank you very much. All right. All right. Should we start now? Are you able to hear me? Deepak, John, Leonid, Matthew. Great, great. So I don't see Vaibhav. Vaibhav, are you back? All right. Now moving ahead, in the similar fashion, you could also import data from Hive back to MySQL. Let's say we have a file called sales.log. Okay, let's say we have a file called sales.log. Let's take a look at Hadoop fs minus ls. No such file and directory. If I say sgiri, all right. I already have a file here and under asgiri called sales.log hadoop fs minus cat. All right. Now there is a Hive table, let's say Hive, that contains this data, and this table looks like this. And so this is like preparing the data in Hive so that we can import it. Okay. Select star from sales. Right? So the data is there in the sales already. So we don't need to prepare it explicitly. Now let's say we have to copy the same data into MySQL. And under MySQL, we have say select star from sales. So we already have a table, so we can delete from sales. Okay. Now we don't have data. So the most important thing you need to remember is while copying back from Hive to MySQL, you have to create the schema of the table explicitly. Okay, you'll have to create the schema in MySQL explicitly. Okay, so first we create the table. We have already created a table in MySQL. You see, we can say describe sales. Okay, so this is in MySQL, and in Hdfs in Hive we already have a table here with the name sales. So we want to take this data from the table in Hive to the table in MySQL. What do? You go to the Hadoop command, and where we say scoop export. Note the keyword called export, and give the URL of the uh, database in MySQL, and we specify the name of the table, and we tell that this is the folder that contains our data. Okay, so we'll have to first find out what is the folder name of the table called sales, and then export the data using that. Okay, so we can use this command to do that. All right, let's try that. Okay, so we have exported some results. Now we can say select star from sales. The data has reached here. All right. So we were able to successfully import the data from Hive to MySQL. In a similar fashion, we can also export data from HBase to MySQL. Okay. Or from Hdfs to MySQL. If you look at it closely, it's nothing but actually exporting data from Hdfs into MySQL. Okay. All right. Any questions at this point? No questions? All right. Now let's talk about another tool called Flume. So Leonid's question is, are there third-party UI implementations of Scoop? Not sure, not sure. I have not seen a UI of Scoop, but good question. Let me also check. Okay, so we'll have to see. Okay, so All right, all right. So Vaibhav's question is how often do we run into scoop in business case, right? Quite often, I would say. Whenever you start a process, so whenever you start a process of importing data from your usual database, you will get into this one. So whenever you are, say, in a business case scenario, let me think about. So whenever you are going to run the data set, so that data set can either come from your traditional databases, or it might come from, say, Apache logs or some other unstructured sources. Okay, so there are 50% chance of data being in relational, even more than that, and therefore you are going to use it quite often. All right, all right. Next is, yeah. All right. So n- after Scoop, we are going to talk about Flume. Unlike Scoop, Flume is a service, and the role of Flume is to pick up data from in any format, whether it's movies or whether it's tweets or whether it's JSON data, whether it's XML data, whether it's binary data. It pushes all of that data into Hdfs. It's great for gathering data from the whole cloud. It helps you gather data from whole bunch of machines onto HDFS. Okay, so how does it do it? Okay, if you can think about it, then you'll have to basically install one agent on every machine in your cluster, which will listen to various events and push the data to the server. Okay, so if somebody has to build such kind of a system which gathers all kinds of data, they will have to write an agent to which all the system events can hook to. For example, syslog is a service which runs on Unix. Syslog is a service which runs on Unix in the background, which gathers all the log, error log, info log, debug logs, all kinds of logs from system wide. Okay, so all the processes in Unix understand what does it mean by syslog, and there is a service called syslog, and all these processes inform syslog about an error, warning, or debug message. Okay, so syslog is running as a service in the background in Unix, and this has been going since like since last 30 years. Okay, now the design of Flume is the same. Flume can run as a service on a machine, listen to all the events, which you can configure into your Java programs, which you can configure into your other programs, so that all of the programs deliver their logs to Flume, which will take these logs and put it in HDFS. So Matthew's question is, does Scoop export to JSON? I have not heard of that one because Scoop has been designed for RDBMS mostly. All right. Now, again, to make Flume really useful and to make it possible to configure everywhere and all kinds of combinations, they came up with a brilliant design. So they call, so on your web server, on your all machines, you install something called Flume agent, and a Flume agent is, okay, so before we get into Flume agent, formal definition, Flume is a distributed, reliable, and available system for efficiently collecting, aggregating, and moving large data from many different sources to a centralized data source. It is from many to one. It gathers data from the whole grid onto a single place or onto a singular place, as in HDFS kind of a place. All right. Now, going back here, so Flume is composed of lots of agents connected together, and each agent is made up of source, sink, and channel. Source is like you are receiving data from some some system which is producing at 1 megabyte per second. Okay, maybe something downloading from internet, some Twitter tweets being downloaded from internet, or error logs receiving. And on the other hand, you have sync. The quality of sync is that in a single shot, it can store in a per if it runs per minute and stores around 60 MB in a minute. So your disk, which is locally available, saves this much data per minute. Now, if you look at this, sync is having a different rate of consumption, while source is having a different rate of production. To match with this, you have something called channel. It's like water tank. Okay. On water tank, you have on one end you have this pump which will push the water into it, and the taps will draw the water from it. So both have different rate of production and consumption. And to fill that bridge, you have this tank. Similarly, here to fill the bridge between source and sink, you have channel. Okay. All right. So now question from Leonid is, how is that different from scoop? Scoop is just a command, okay, which schedules MapReduce. In case of Flume, Flume is a network of agents. Agents are services running in the background. All right. Now, if you see the design of source and sink, not source, sink, and channel helps you bridge the gap between source and sink. On the other hand, the whole design of source and sink is such that one source of one agent can hook into another, like the way USB can either hook into the computer or hook into a car charger, or it can also hook into your normal charger, right? In the similar manner, if there are other agents, the source can hook into them. Okay, so source can hook into other agents and bring data to here. Okay, so the behavior of Flume is always from source to sink. Okay, so source and sink can be connected together to deliver something. Similarly, you can also do things like one source can write to multiple sink. Sorry, one sink can write further to multiple sources, and then the multiple sink can also write back to single source. All right. You can easily visualize that if you have say 15 web servers and continuously they are all producing a particular log as in history of things, at every second it's producing something. Now you want to bring all these logs continuously into HDFS so that your developers can quickly churn the data. Okay, and that kind of role is played by these hooking up agents with one another. All right. So the sources can be in the form of tail minus f. Anybody? What does tail minus f do? No idea? So tail minus f continuously produces the data which is being continuously produces the data in the meaning that if there is one process writing to your file continuously and you want to see what are the changes happening to this file, you can say tail minus f. It continuously spits out the data on your screen. Okay, so tail without minus f gives you the last record. That's correct, Leonid and Matthew. Okay, normal tail command does that, but tail minus f continuously monitors a file and prints on the screen. Okay, so such kind of things which can keep on producing the data continuously can be a valid source. Similarly, log4j and syslog. All right, Flume's node can be arranged in arbitrary topologies, and there's always a node running on source machine. All right, now let's have a look at an example. What exactly are we going to do? What are we going to do here? What are we going to do is we will we will run an agent which will listen to our events as service running on a port. So our agent will be running as a service listening on a port, and whatever we tell it we tell it it will push that data to Hdfs. Okay, so basically it will be a socket connection. Listen to the socket, and then push it to Hdfs. Okay, and in between listening to the socket and Hdfs, there will be a channel, and this channel is not too much required for this example. Okay, is memory based. The channel is going to be memory based. Is it clear to you? This is what we are going to do next. All right, so our agent is going to be like this. This is what our agent is going to be. Sounds good? Let's have a look at it. So we define something called flume.properties, in which we will write the configuration of each of these parts of agent. Okay, so let's say we have agent with a name called A1, and it has got only one source right now, but if you have multiple sources you can put comma and give their names. So the name of sources for A1 is R1, and sink is S1, and channel is C1. Now the definition of R1 is that it's a netcat. Netcat is a Unix command which can make you listen to a particular port and read the data from there. So it's a netcat command which is listening to this port and will be giving in SDT out whatever people write to it. Okay, and so if you run netcat locally, I will show you this. So I say netcat localhost and port is this. Oh, sorry, netcat means NC. So NC minus help. Okay, All right, never mind. So yeah, so you can basically say that listen to this particular port by defining netcat kind of a data source. Okay, and uh, uh, on the other end, the data which we are going to write it into Hdfs, which means our sync type is Hdfs, and this is going to be our path output folder. Okay, output folder is going to be this. And next is that we define the channel. Channel is going to be the memory. So we are not saving the channel into disk. The capacity of channel is this much, and after which it will stop accepting the data from the source. Okay, again we have told channel r1 who is our r1's channel. So all of these components also know each other. R1 need to know about its channel, as well as sync needs to know about channel. All right, so steps are also have a look at this diagram, this file there. So I will have as Giri. So you can see there is a conf file. Under the conf file you can see a conf file, and then you can see Flume properties. Okay, you can see all of these things defined here. And also let's keep an eye on this particular service. Okay, let's keep an eye on this HDFS file. Okay, you can see that these are the particular files. Let me just delete them. All right, now let's run this agent. And how do we run the agent? By executing a Flume agent command. Here we are saying that Flume ng, and then our conf folder is here. Okay, so you can see that we are saying conf file is this, and conf folder is this. Conf folder is conf, and conf file is this, and the name of the agent is A1. Okay, as we defined in the. Now it's ready. It's saying that it's listening on this particular port channel, this particular port called 4444. Okay. Now the moment we start writing to it, the way we write is telnet localhost and 44444. Why? This correct, right? Oh, not localhost. We have to, because we are on Hadoop 2. Okay, and the service is running on Hadoop 1. Even if we try to connect from here on Hadoop 1, because we have bound it to localhost, it may not be possible. Let me try again. So it's saying connection refused. So we'll have to go to Hadoop 1. If we had put here, right, if in this config, if in this config the IP address configured would have been 0000, then you can connect to this service from anywhere. Okay, you can connect to the service from anywhere. Now we can say telnet localhost and 44444. Now it's connected to our agent. Right now, telnet command is the Unix command which lets you write or talk to any service. Right now, it's letting us talk to our agent which is running on this particular port. And here we can start writing data, and this data is continuously being pushed to HDFS. So we are continuously writing data, and the data is going into HDFS. Okay. Similarly, there could be hundreds of people who are producing data. They could be writing to HDFS. Now you can see that the data is being generated. If you click on any of this, you can see that the data is being generated. All right. Make sense? So if we start writing Webhub, Leonid, Matthew, and John, Deepak. So, alright, if you go back to our file system, you will see that there, okay, so you can see John, Matthew, Leonid, Deepak. Alright, now Weber must be in a separate file. Yeah, you can see Weber is here. So it keeps on forming automatically, it keeps on creating these small snippets of data and keeps on pushing it. Now question from Matthew is, what is the difference between capacity and transaction capacity properties? Okay, capacity is the size of the pipe here. Capacity is total how big the pipe is going to be, how big this space is going to be. Because as soon as that gets full, it will not accept anything from the source. Okay. Transaction capacity is number of records that can be handled per second. Right? Okay. So that was a question from Leonid. Sorry, it wasn't Matthew. All right. Great. All right. Now, that was how we push the data from a running service continuously into Hdfs. Also, all right. Sounds good to you? So when the capacity is reached, as I was explaining you, when the capacity is reached, what would happen is it would stop the source. So it will start giving the error that I cannot take any more data. Okay. And the capacity will reach only when there is a huge difference between rate of production and rate of consumption. The rate at which the data is being produced by source and the rate at which the data being consumed by sink. If there is a huge difference, then this capacity will be hit. All right, this number is, I think this number is, I think it is in kilobytes. Okay, it's kilobytes. All right. Sounds good to you? Alright, now moving on. The next thing which is very important in case of Hadoop is Uzi. Uzi is a workflow scheduler that helps you manage large number of jobs. Okay, I'll explain to you why exactly you need. So it's a workflow scheduling system to manage Hadoop jobs. It's a Every job is a directed acyclic graph of actions. Okay, and I'll explain to you what does it mean by DAG. It also provides you a coordinator, which is basically a recurrent jobs triggered by Uzi. So if you want to run your job, if you want to run your job, you can other than running it by yourself, you can ask coordinator to run it for you. And this coordinator, which is Uzi coordinator, can run it based on time frequency as well as data availability. Uzi is well integrated with the Hadoop stack, and again, like everything in Hadoop, it's a scalable, reliable, and extensible system. Now, Uzi's workflow is a DAG. Just like you have ant, in case of ant we have great number of tasks which can be stitched together, and you can comfortably run anything without having to worry about what else we need to run, right? So you create this dependency graph saying A depends B depends C, so when you run A it runs C as well as B. Okay, in the similar manner you can see that the task number 5 depends on task number 11, and imagine you can say that going to office, which is task number 5, is getting ready, taking a bath, which is 11. And for taking a bath you need to you know do the brush and other things. So there is a full dependency graph. Or wearing the cloth depends on first wearing the shoe, wearing the trouser, and then wearing the shoes, and so on. Okay, so you can always create this dependency graph. Probably in our lifetime, in our life, we keep on doing it all the time, creating this kind of a dependency graph, that for doing this kind of job we need to do other things, and for that we need to do something else, and so on. This is called DAG. All right. So the examples of DAG is a project plan, and Ant script, Maven script, Make script. All of them have DAG. So Uzi is a workflow that lets you execute the commands, that lets you stitch a DAG and then execute this DAG on uh, execute this DAG either periodically or manually or based on some data changes. All right. Now this might look intimidating for you, but don't worry, this is not something you have to write. All right. Let me just take it out and explain to you. So the way you define your Uzi workflow is in XML. All right. So is it visible? The font is visible to you? So in this, you can see that we are defining our map reduce job. This is the main work that we are trying to do. We are saying, Uzi, please execute our map reduce job. This is our output directory. This is our input directory. You can see output directory, input directory, reducer task, mapper task. This is under configuration. This is the job tracker, and this is the name node. Okay, so this information we stitch it in the map reduce XML, and then we stitch the whole workflow. So the whole workflow typically starts, the top node starts with workflow app, and after that we define that this is the starting point. And what does it mean by starting point? It's an action with the same name called word count. So when workflow start, it goes to starting point, and then this particular node executes this map reduce task. Okay, and when it finishes, go to the end, go to the end. When it gets killed, you go to this particular element. So what exactly are we trying to do? We are trying to define that how is something going to get executed. What will happen in case this fails, and so on. So this is how we are going to, this is how a Uzi workflow is defined. Okay, this is how an Uzi workflow is defined. Alright, here there is only single task, but there could be multiple tasks in case of Uzi. Let's have a look at. So this task were easier. Start the process, execute map reduce word count, and then end it, or if it goes error, go to kill. Similarly, if you have a complex workflow like this one, where you start the process, execute first work, and then execute second and third parallelly. Second and third will not wait for each other to finish, but join will wait till both of them have finished, and then it will execute final. All right, and the the all right, the XML looks like this. It starts with workflow app. It starts with workflow app. It has got multiple actions this time. but start to point is first job. First job when it finishes, it goes to fork. Inside fork, it executes two paths parallelly, and then it individually both of these paths reach to join. You can see okay to join, okay to join. So it goes to join, and join executes final job, and final job is a map reduce job. You can see that. So basically we can stitch these kind of complex workflows where we want some things to be executed parallelly and something to be executed in sequence. Okay, so in a typical case there could be multiple things, as you will see that first import the data using SQL. Sorry, first import the data using scoop from SQL, then clean up the data, reformat the data, separate it by comma instead of colon, and then clean up the dates. All of these tasks are going to be individually action inside Uzi. All right, so this is how you define Uzi. Similarly, you can also define the same thing using the browser. All right, let's first try to execute an Uzi workflow. The Uzi workflow, the way we were defining our XML, you can define the XML and put it in your Hdfs folder here. Like for example, we have kept something called examples. So you can upload everything onto the server like here. So this is your full project. Okay, this is your full project. Under this is your one Hadoop project. Let's say your job is MapReduce. Okay, under this you define your workflow called workflow.xml, and this is how it would look like typically. All right, here these variables are coming from property file. I'll show you. Okay, now this workflow is executing many tasks. You see, it's saying sample mapper, sample reducer. Where is the definition of these sample reducers? It is in the lib folder. So your map reduce jar, whatever you have created, you put it in this lib folder and refer it from your workflow.xml. Okay, and then once you have done that, then you create a job.properties. This job.properties defines where is your name node, where is your job tracker, and some queue name, and then the workflow application path. Okay, meaning this path should have workflow.xml inside it. This path should have workflow.xml inside it. This is where it is. Okay, so workflow XML should be inside the path which you mentioned in job.properties. Job.properties is all of this data is required to be in the Hdfs, while job.properties have to be locally available to you. Okay. Now, how do we start our process? How do we start launching a Uzi process? And the way we do is using Uzi job, we say that this is our Uzi server, and we are giving this particular map reduce. We have downloaded this job.properties locally as well. So job.properties have to be locally available, while your jar code, script files, all of this will be inside the config. And the way you run is, okay, the way you run is you go to the command prompt and run the Uzi. It says that this particular job.properties is not found. Okay, we can copy that from Hadoop, and we can say fs copy to local. Okay, and we can say this. Okay, and I've copied to my Flume folder. Let me just move it out from here. All right, now I can run the same Uzi command. Like you can see that I'm saying this is my Uzi server. This is my configuration. This configuration contains the reference to my Uzi application folder. Uzi application folder would contain workflow.xml containing the description of what other things need to be executed. So it says that your job has been executed. All right. Now let's have a look at here. So you can see this icon. That's what shows you what exactly is running. This is what we have just executed. Okay, this is what we have just executed. It's executing, and something is going on. All right. Those who are very much intimidated by all of this UI, no need to worry. There is a beautiful UI available here. Okay, for doing the same thing what we have done locally. You can go to workflows and create your own workflow, or let's say you create your workflow. All right. As part of workflow, say first of all you want to run scoop command to import data. Okay, let's say import data from SQL, and here you write some import command. The SQL scoop import something, right? That's what you write. That you write here, and then you can simply say do save. You can say done. All right. If you want to parallelly import from another database as well, you can pick up scoop and drag and drop just on the same thing. So you can say import from MS SQL. Okay. Now you can see that parallelly as the task is started, one part is going to download from MS SQL, other is going to download from this thing. Now on join, when both of them have finished, let's say what you want to do is you want to run Hive command. Okay, here will go your Hive command, and you will basically upload your Hive script into an Hdfs. Okay, you can just pick up this. Let's say this is your Hive command, and you say okay. Now you can see that we imported data from scoop, then Hive, and then we can at the end, once Hive finishes, we can say things like MapReduce. Okay, not like this. I will just say MapReduce and my MR. Okay, now you can see that this field jar name is required. We'll just go to user and student, and then asgiri. Where is asgiri? Asgiri, and then there'll be something care count. All right, you can see. Now you can see we have made this beautiful uh, MapReduce task using a nice beautiful UI. Okay, so typically this is how you will be designing your project. Okay, so we have saved our workflow, and then we can execute our workflow from here. You can select this one and say submit. All right, right now it will fail because we have not specified parameters correctly. This is how Uzi works. All right, so Uzi is executing another task in parallel, and that's all. If you want to see the status of Uzi, you can say, all right, let me just try to show you the status. What does it say? Okay, what does it say? It says it's preparing, it's still preparing. Okay, sounds good to you? Right, great. Now this is something which is running already, which we just started. All right, So this is how you execute your MapReduce job. Good. So we have already gone through this UI. Let me open that UI again. Yeah. So in the workflows area, you saw a lot of things, right? You saw there was MapReduce. You could run Hadoop streaming, as in run any script as map and reduce. You could run Java program on as part of your job. You could run Pig. You could run Hive. You could run Scoop, Shell, SSH, and you could also run this CP. Okay, you could run any of these tasks. Okay, what is fork in case of UI is same as what we described here. So like this, when you want to fork at many places, you want to run multiple tasks parallelly. Okay, so as you can see, after start, it got forked into two branches. One branch was for importing from MySQL, other was from MS SQL, and then it got join here. This is join. All right. So the way you create fork is you drag the task, and whatever parallelly you want to execute, you drop on that. Okay, you drop exactly on top of that, and then this newly dropped task will be there. I'm just You can see we created just now one more fork under fork, fork under fork. See that? So whenever we want to more than one thing to be executed parallelly, then we use fork. All right. These are the actions, various actions. Good. So that was Uzi. All right. Now I want to take you through Mahat. So Mahat is a scalable machine learning library written on top of Hadoop, and it's driven by a paper by NGETL, NG and Company. And the paper was MapReduce for machine learning using parallel on multi-core. Okay, so it started as a Lucene sub project, but it became top level project in April 2010. And Mahat literally means the keeper or driver of the elephants. So what does it, before we dive into Mahat, let's understand what does it mean by machine learning. So basically, the complex tasks such as machine learning can be done easily by using standard libraries like Mahat. Okay, so what is machine learning? Machine learning is a branch of artificial intelligence for design and development of algorithms, and essentially computers predict and evolve based on empirical data set. If you want to have a look at it, have a look at this video, and you will be amazed at the level of sophistication in machine learning when you look at this. Okay, so not this one, this one. Okay, so basically this video shows you that how does a computer learn to play Mario and how well it plays. So I'm sending this link to all of you. Okay, so do visit in your full free time. So basically in that video, it shows you that the the researcher was able to make the program learn to play any game it wanted. Okay, any game it just hooked the program to Mario memory, where the Mario is running in the memory. It hooked that program, and it told the program that this is the score, and your objective is to increase the score no matter what. So program automatically figured out, and also program was told that you can press all these keys like this. That's all. Program was he wrote a generic program which could read the memory in Mario, and not Mario but any program, and tell that this means winning, this means losing. Okay, and that's how he let the program learn any game by itself without coding a single line. And the program learned how to play all these games in a far more efficient the program was far more efficient at playing various games, so much so that it found bugs in Mario so that it could actually win in all possible cases. So it automatically figured it out. Nobody had to program anything. So it's for design and development of algorithm. Okay, so you have a look at this video and you will realize what I'm talking about. It's more like a scientific, I mean sci-fi fantasy came true. All right, so have a look at that. So there are multiple kinds of machine learning. One is supervised. Supervised means you tell the program that this means winning, this means losing. Okay, you have a clear data which says that this means losing, this means winning, this means yes, this means no. That is called, if you have this kind of problem, and your objective is to find out whether your software can learn from this history and start predicting whether, given an input, can it tell me it means winning or losing? If I've given it a lot of data saying this data means winning, this data means losing. Okay. Similar to that, your spam filter. If you give enough data to your program and tell it that this email means spam, this email means not spam. Now, can this program automatically learn from all of this to a level such that I can give it an email and ask it that is it a spam or is it a legitimate email? So so when you have this kind of clarity and that's your objective, it is called supervised learning. A lot of time you don't want it. Sometimes what you want is that you don't neither you have data with a clear winning or losing kind of possibilities. You have something like a huge set of emails saying, and your objective is that given this inbox, can you quickly can you quickly create buckets of data? Okay, can you segregate these emails into 5 separate buckets like the way you see in Gmail inbox? There is social, there is uh, there's that. Basically that's exercise called unsupervised learning. You essentially tell the program that automatically create these many groups. Okay, now in case of semi supervised learning, you generally have unlabeled data for training, typically small amount of labeled data with large amount of unlabeled data is given, and you have to figure out these patterns. That is called unsupervised learning. All right. Now there are many applications to machine learning. You might already be seeing lots and lots of applications of machine learning, starting with recommending friends and telling object properties. All right. So there are lots and lots of applications of machine learning. You can have a look. I mean, almost everything can be accomplished using machine learning if you have enough of data. If you have enough of data, okay. Now, the machine learning tools which do the prediction, which do various kinds of analysis, they are in this is how they have evolved. When you have few lines of data, you did most of the analysis on the whiteboard. If you had few kbs of data, then you used MATLAB, Octave, R for processing. If your data started going into GBs, then you move into NumPy, SciPy, and all of that for analysis. Now, at the moment you hit GBs, the visualization tools, the tools which you use for visualization become different from the analysis. When your data is small, it makes sense to visualize them. While when the data starts growing bigger, the visualization tool cannot be same as analysis. Because in case of petabyte data, you don't really need visualization, because the visualization will not make any sense to the human eye. Okay, so you can do the analysis and visualization of data using these tools. Okay, and the moment you start going beyond gigabyte, which means your RAM is not sufficient for processing of data, then you have to move to bigger tools such as Mahout, Giraffe, and MLlib. Okay, these tools run using multiple machines and give you the results. All right. Now in this, you also have got MLlib, Spark R, and Spark R, and then we have GraphX. All right. So that was all right. As part of an exercise of Mahat, what we will do is we will try to build a recommender. What does a recommender do? Given the ratings of lots of people, it produces the ratings of recommendations for various people. Recommendations means what will these people like to watch. All right. So let's, all right. So recommendation example is this is okay, right? There are many algorithms which produce the same result. And do you want to do it today or do you want to do it later? Yeah. Vaibhav, Matthew, Leonid, John, Deepak. Should we run through the example of Mahat today or tomorrow? All right. So anyway, we will run through this recommendation example tomorrow. Okay. And in case the time doesn't permit us tomorrow, we might have to extend by maybe half an hour. Tomorrow's class might get extended by half an hour, which means it will finish by 10:30 or maybe 10:45. Okay. I hope that's okay with all of you. We'll take maybe 15 minutes break in between. Yes, tomorrow will be the last date for the class, Leonid. All right. All right. Great. Now the assignment for today is try importing all of these import exercises, whatever I did for you. Just do it by yourself. Okay. Do it by yourself at least once. It will give you enormous confidence. And otherwise, you will just forget all of this. So, importing all of these 3, 4 exercises which we did hands on today, try doing it by yourself, including Flume. Okay, that will give you a really big confidence in terms of execution. Yeah, we can take 2 breaks tomorrow. That makes sense, Vaibhav. All right, we can take a break at maybe 1 hour each, maybe 1 hour and 1.5 hours. All right, great, great. So we'll see you tomorrow at the same time. Bye bye. Have a good day. All right.